Welcome everyone, and thank you for joining me today for the last video in this series. In this last video, I'll highlight lessons learned. Starting with code development, I'll describe how coding assists help in this work. Probabilistic output, for anyone who have used LLMs realize the output of the LLM are not deterministic, and this can complicate the development process. In LLM versus in code, with the availability of LLMs, a developer now has a choice of implementing a function in the LLM or directly in the code. I'll describe two situations where I faced this decision. Latency. Performance is always a critical factor. We'll discuss the system's response times and an approach taken to minimize delays. We'll end with a summary of key points, consolidating the main takeaways from the entire video series. Now, let's get started with the first topic, code development. From my perspective, there is value in task-specific coding assistance. Here are three examples of what I mean. First up is ChatGPT OpenAI Playground. This tool was incredibly useful for drafting initial prompts and testing them iteratively. It allowed me to quickly iterate and refine the logic behind the prompts, which saved significant development time. The Playground provided initial code for calling the API. This was useful for getting a prototype up and running quickly. Once I made it past the prototyping phase and wanted to write more durable code, I used Perplexity AI for generating starter code, especially for LangChain and LangGraph projects. These are new and quickly evolving projects where the API can change over a short period of time. I found Perplexity often produce better examples than GitHub Copilot. I believe this is due to the way Perplexity operates, i.e., basically doing a retrieval augmented generation or RAG on current web content. In the case of GitHub Copilot, it often produced code examples based on a deprecated API signature. I suspect that this may be due to how the Copilot is trained on content in public repos in GitHub, where there may be fewer examples of up-to-date API signatures. Another benefit of Perplexity are the references provided in its responses. However, not all references it provided were relevant. Some were spot on, while others did not add much value. This does not imply GitHub Copilot was not useful. Once I was in the mode of heads-down coding, GitHub Copilot greatly facilitated hands-on, focused development, or, as GitHub likes to describe it, it allowed me to stay in the flow. I used it for setting up the VS Code dev container configurations, which took several iterations over the course of the project, generating boilerplate code, creating unit tests, refactoring existing code, understanding my code base. Using its new Copilot Edits feature, which does coordinated edits across multiple files, reduced the tedious work of code refactoring across multiple modules. When it comes to generating Python package-specific code, Copilot does this well for long-established stable Python packages such as Pandas and NumPy. Overall, these tools complemented each other, allowing for faster development. Now, let's move to the next section on probabilistic output. In this section, I want to highlight a fundamental challenge when working with large language models, probabilistic outputs. Let's start by recalling how traditional application development works. In most cases, the systems we build are deterministic. This means the same action will consistently produce the same output. For example, if you run a SQL insert query, the database is updated exactly as expected. Or, if you send data to a web page, it reliably appears on the web page. However, this principle shifts when we move to Gen AI applications. Here, the outputs are probabilistic, meaning that the same prompt can yield different outputs each time it is executed. This variability can be useful for creativity in generating diverse responses, but it introduces complexity into the development process. One of the biggest pain points is that it makes it difficult, if not impossible, to reliably reproduce errors. Without consistent outputs, performing root cause analysis can become a frustrating process. This shift forces us to rethink debugging, testing, and even how we structure our workflows. In the next few slides, I'll show how this manifested in this work. This slide visually demonstrates the core challenge of probabilistic outputs when working with LLM-based systems. This is an example of same input, different output. On the left and right, we have two outputs generated by running the same input file, data/forward_list4.txt. The initial puzzle setup, vocabulary generation, and embedding steps are identical. However, notice the differences when the embed vec recommender returns its recommended words. On the left, the recommended words are clap, peal, roll, rumble, all associated with sounds like thunder or resonant noises. On the right, the recommendations are comb, dig, root, sift. This reflects a different semantic connection, this time aligned with searching or examining thoroughly. The key point here is that although the underlying model and process remain the same, the candidate list sizes differ, 81 on the left, 77 on the right. This small difference in candidate lists results in an entirely different output. This variability can be beneficial for creative tasks, but for application development, it introduces a level of unpredictability. It highlights how hard it can be to debug and reproduce results consistently. For example, if I thought the left side output was incorrect, I would not be able to reproduce the situation consistently to do root cause analysis. To mitigate this, developers often need to implement strategies like temperature control to limit randomness, or leverage deterministic fallbacks for critical paths, or store and analyze outputs to track patterns and refine prompts, or all of the above. This is an important aspect to consider when integrating LLMs into the mix. This slide further illustrates the variability of LLM outputs by summarizing the results of 4 separate test runs on the same 10 puzzle test cases. Each table represents a summary of 10 test cases for solving puzzles. The key metric here is the number of puzzles successfully solved out of the 10, highlighted at the top of each table. In test run 1, 4 out of the 10 puzzles were solved, a 40% success rate. Test run 2, 6 out of the 10 puzzles were solved, achieving a 60% success rate. Test run 3, 5 out of the 10 puzzles, resulting in a 50% success rate. And in test run 4, 4 out of the puzzles were solved, matching the first run at 40%. I'll note that 10 test cases are not sufficient if this was a real application. For a real application, we may need hundreds of test cases. For this video, I'm using 10 test puzzle cases for ease of presentation. While the input data and process remained consistent, the outputs varied with each run, reflecting the probabilistic nature of the LLM. This variability not only affects overall performance, but also impacts the confidence and system reliability. For example, in test puzzle 0, it was successfully solved in all test runs. Test puzzle 1 was successful in run 2 but failed in runs 1, 3, and 4. Test puzzle 7 failed in all 4 test runs but failed in different ways, only getting 1 correct group in 1 run, another run getting 2 correct groups, and in 2 runs finding no correct groups. The takeaway here is that achieving confidence in results requires multiple iterations to get a measure of overall performance. Planning will be needed to define a robust test strategy. This may require consulting with data scientists, whose day job is to deal with probabilistic outcomes. They can assist in defining the appropriate testing strategy. This slide highlights two specific examples of intermittent hallucinations and misgroupings that occurred during testing. The issue on the left describes a rare occurrence where the LLM hallucinates puzzle words. On one occasion, the LLM hallucinated two words, astute, clever, that were not part of the original puzzle vocabulary. Essentially, the model hallucinated terms that fit the context but did not ensure the words were valid puzzle words. Since I started this project 2 months ago, this has happened only 3 times, reflecting how infrequent but unpredictable these hallucinations can be. The issue on the right describes a different kind of error, where the embed recommender returned a group of words, crowd, flock, host, masculine, that lacked a unifying connection. The model correctly grouped crowd, flock, host, but the word masculine introduced a semantic mismatch. This type of misclassification only happened once thus far. These examples illustrate that while these errors are rare, they can still pose challenges. Hallucinations may introduce irrelevant outputs. Misgroupings can undermine the reliability of the recommender system. To address this, we may need to address more validation checks in the process. We now shift to another set of lessons learned. This slide highlights an important distinction between putting functionality in code versus relying on the LLMs for a particular function. Ava kept track of mistakes in a list. Originally, this mistake list was part of the prompt when generating a word group recommendation. On the left, you can see part of the prompt instructions used to guide the LLM. The instruction is explicit. Do not include word groups that are known to be invalid. Below that, you see the list of invalid groups that have been encountered. There are 3 invalid groups, meaning 3 mistakes have occurred. Despite this clear instruction on the right, we see the 3rd and 4th invalid groups are the same from the connection puzzle perspective. The only difference is word order. Since this was the 4th mistake, that particular puzzle solution ended with a failure. This 4th group should not have been generated. To address this issue, I could either refine the prompt to make sure I include instructions on word order, or I could move the prior invalid group detection into code. The next slide describes the code approach. This slide demonstrates the transition from the LLM to Python code to enforce invalid group detection. On the left, you can see the Python code. The function compute_group_id takes a list of words, sorts them, and computes a unique hash using MD5. This creates a consistent identifier for each word group regardless of word order, allowing for easy detection of duplicate invalid groups. When a new invalid group is recognized, the tuple consisting of the unique hash and words are appended to a list of invalid connections. In the last code block, the code checks if the group already exists in the invalid connections by comparing the unique hash stored in the tuple's first position. On the right, we see how invalid groups are now recorded. The invalid group includes the unique hash value. Since implementing this function in code, I have not seen repeated invalid groups with different word orders. By migrating this logic from the LLM to Python, the process became more deterministic. Python consistently enforces the rules without probabilistic behavior. It's traceable and debuggable. Errors can now be analyzed at the code level rather than interpreting ambiguous LLM decisions. In the next slide, I'll describe the situation of moving functionality from Python code to the LLM. This slide focuses on the transition from Python-based logic to an LLM-driven workflow for managing the puzzle solver's workflow decision-making process. At the top, the diagram illustrates the overall workflow. This was described in the video about Ava's planner component. Originally, the logic for routing processing all resided in Python code. After viewing a talk about using the LLM to manage the sequence of actions in the workflow, I decided to move this function to the LLM. How the LLM does this function was described in the design and implementation video on Ava's planner component. Since doing this refactoring, I've run Ava hundreds of times. I've not noticed the time when the planner made the wrong decision in workflow routing. I'll end with this thought. Here is one of my favorite quotes from the first Jurassic Park movie. This is where Jeff Goldblum's character, the mathematician Ian Malcolm, says, "Your scientists were so preoccupied with whether or not they could, they didn't stop to think if they should." The point here is just because we can do something in the LLM, should the LLM do it? This highlights the need to understand the trade-offs involved with deciding where to implement functionality, in code or in LLM. While migrating logic to the LLM is exciting and flexible, it introduces complexities that may not always be necessary. In certain cases, keeping deterministic logic in Python would have been simpler and more predictable. At least for Ava, for now, I'm keeping the LLM-based workflow. This slide highlights another key lesson from our development process, addressing latency in large language models. LLMs often introduce significant delays, which can severely impact overall performance. The takeaway here is that by leveraging asynchronous operations, such as Python's async IO library, we can substantially reduce runtime by overlapping tasks. On the left side, you can see the latency for the first implementation. In the original process, generating vocabulary definitions sequentially took approximately 45 to 55 seconds. This bottleneck occurred because each word's definitions were generated one after another. On the right side, you can see the results of refactoring the code to support asynchronous execution. With this refactored code, vocabulary definitions were generated concurrently. By utilizing the async IO package, definitions for all 16 words were generated simultaneously, cutting total processing time to under 5 seconds, a significant improvement. Async IO enables concurrent executions of IO-bound tasks, such as REST API calls. This approach minimizes runtime by allowing multiple IO operations to proceed in parallel, transforming workflows to be more efficient and responsive. To close this video series, I want to summarize the key takeaways. The videos describe building an agentic virtual assistant to help solve the New York Times connection puzzle. The approach taken was based on agentic concepts, and the agent's operation is focused on a narrow task-specific context. It is not a general-purpose tool. An agent has three major components: memory, tools, and planner. The connections puzzle agentic virtual assistant Ava took advantage of LLM models to do diverse functions such as workflow management, word extraction from an image, and recommending the 4-word groups using 3 different approaches: embedding vectors, raw word analysis, and handling the specific one-away error situation. Ava was built using the LangChain and LangGraph frameworks. Ava's workflow operation is based on a finite state machine concept. This workflow is driven by natural language description. Ava, in providing assistance, utilized specific tools for puzzle setup, word group recommendations based on the 3 different approaches: embedding vectors, raw word analysis, and one-away error analysis, applying feedback from the connection puzzle, and supporting a manual override function. And we covered lessons learned. This included use of multiple coding assistants in the software development, handling LLM probabilistic outputs, decision factors for implementing a function in code versus the LLM, and finally, mitigating the LLM's long latency. I appreciate you taking the time to view the videos. I hope you were able to learn something new. If you found this content useful, please like and subscribe. Thank you.